Entropy in welding refers to the measure of disorder within a system, particularly as it relates to the temperature of liquid metal at high levels. It is a thermodynamic property that represents the total heat content of a system. According to the second law of thermodynamics, entropy increases as atomic structures become more disordered. In the context of welding, consider the fusion process between the weld zone, the epitaxial grain growth, and the base material aches. The epitaxial grain growth area in welding occurs because the high heat and the chemical composition of the base material are similar enough to facilitate bonding with the welding metal. At this high temperatures, some of the base material is completely melted and mixed with the weld metal. We will go over the weld zone and the heat-affected zone, has. Let's start with learning a scientific word, epitaxial growth, which means grain growth from base metal into weld zone. Always visualize the metal's grain structure in 3 dimensions to better understand how a cross-section would appear when sliced in 2, allowing you to visualize the internal grain geometry accurately. Grain junction between grains is their boundaries atoms mismatched in orientation. You can see them in their unique form and color identification. Each grain has its own boundaries and unique form. In image 1, the epitaxial grain growth is evident in the area marked by the arrow. It shows a transition where the grains align and grow from the base material into the weld zone. This type of growth is characterized by grains extending from the heat-affected zone into the molten weld metal, maintaining the crystallographic orientation of the base material. The visible grain structures suggest that the high heat input and chemical compatibility between the base metal and the welding material facilitated a seamless fusion, leading to epitaxial grain growth. This process is crucial for achieving structural integrity in the weld joint. In the 2A region marked in the image, the coarse grains are indicative of a heat-affected zone, chassis, subjected to high thermal energy during the welding process. These larger grains form as a result of recrystallization and grain growth under prolonged exposure to elevated temperatures. Coarse grains often reduce material toughness and ductility in the affected region, but are a typical feature of high-energy fusion welding processes. Their presence here demonstrates the significant heat gradient and thermal effects within the weld area, which facilitated epitaxial grain growth near the fusion boundary while enlarging grain structures in adjacent regions. Access to a transmission electron microscope, TEM, offers unparalleled advantages for advanced material characterization, enabling the observation of atomic structures and dislocations with extraordinary resolution. This state-of-the-art technology facilitates precise analysis of atomic dimensions and the formation of atom crystalline structures, which are beyond the capabilities of commonly available instruments. Given that metal atoms are significantly smaller than bacteria and protein structures, direct visualization is impossible without advanced equipment like the TEM. The atomic diameters of elements, typically on the order of 1 angstrom, along with their unique proton counts and discrete energy levels, highlight the critical importance of always touching on fundamental properties of metal atoms.